Okay, here we are. We're just going to learn some of the applications of Boyle's law, Charles' law, Gay-Lussac's law. Last class you did some graphing and did an online lab, and hopefully have learned the relationships. On the previous pages you have some notes on Boyle's law, which basically says that as pressure goes up, volume goes down, or vice versa. Here we're talking a little bit about Charles' law, and as temperature goes up, volume goes up, or vice versa. It's a direct relationship. So now we're going to apply these into some calculations. Now, I'm going to tell you something right off the start. The way that I teach this might not be the way that some of you have learned it either in the past, if you've gone to another school, or I know some of you are going to tutors. And the tutors are going to teach you a formula, and I have to admit the formula always works, but it's just plugging numbers into a formula, and it doesn't make you think. Okay, so I'm going to teach you guys how to think, and if you know how this works, you'll always remember it. You're going to forget the formula, but you're always going to learn how these things work. So I'm starting here on page 192, applications of Boyle's law, Charles' law. And I've given you some a little bit of relationships here. As pressure goes up, that's what the up arrow means. Volume would go down. That was an expression of this is being temperature and mass constant. So that's Boyle's law. I forgot the arrow here, but as pressure goes up or temperature goes up. Okay, and that was one that I asked you to consider the other day. That's actually Gay-Lussac's law. And the last one is as temperature goes up, volume goes up. Or vice versa. Okay, so we're just going to take these relationships and see how they work. Okay, so let's go back on to the next page, page 193 in your notes. If I'm using this in future years, the page might change just a little bit. But here's a first example, and you can there it is. You can read it there. A sample of oxygen with a volume of 500 mils at a pressure of 101.3 kilopascals is to be compressed to a volume of 450 mils. What pressure is needed to do this? Okay, if temperatures, that's fairly important that you're going to keep the temperature constant. Here's what I would like you to do in order to communicate this. First thing I would do is write down your conditions. So the initial pressure, P1, is 101.3 kilopascals. Your P2, you don't know. It's asking for that. If we look through, is it at what pressure? At what pressure is needed? Okay, so that's going to give you the pressure, the equation. Okay, so V1, if we look at it, is 500 milliliters, and V2 is equal to 450 milliliters. Now, I would start with an equation, P2, you know I like equations, P1 times the volume factor. This is the only time I'm going to write it out. For me, if you just use VF or TF or whatever, that's fine. Now, we're going to put in our initial pressure, 101.3 kilopascals. Now, what's the volume factor? Well, if we look at this, we're going to ratio it against the volumes. Okay? And here's what I would like you to do. We can see here that the volume is going to go down. So what happens to the pressure if the volume goes down? So think back to your Boyle's law. That's an inverse relationship. So the pressure is going to go up. So we're going to put these in a ratio that causes the pressure to go up. Okay. If you look at that, there's only one way that can happen. If I put the 500 mils over the 450 mils, that number is going to be greater than 1, and so my pressure will go up, and you'll get the correct answer. So that's what I want you to do. I want you to think about the law as you're putting these things in. If we do the calculation, you've probably done this in your head and realize that that's about a roughly 16% increase or something like that. Gas laws are really nice that way because we're dealing with numbers near 100. Anyway, I worked it out and it was 113 kilopascals. Okay. Next problem is very similar. For you to practice, you could work out that at your desk. Just switch off the video for a minute, try this problem, and then I'll come back to it. Okay, so hopefully you've switched off your video and you've done this problem and you've got an answer. This one is actually quite easy. It's very similar to the last one we did. We're going to write down P1, P2, V1, V2. My V1 in this case was 440 mils. My V2 was 880. Those are nice convenient numbers. P1 was 98.6 kilopascals. So same equation. P2 is going to equal P1 times a volume factor. Okay. V1 is 98.6 kilopascals. Yes, your units have to be in there. And if we look at it here, my volume is going up this time, so my pressure has to go down. So I'm going to put the smaller one over the larger one. So that'd be 440 mils over 880. Hopefully you recognize that that's 1/2. And so 1/2 of 98.6 is 49.3 kilopascals. It's as simple as that. You didn't even need a calculator. Okay, switch the video off again and try this practice one. It's slightly different from the previous ones. Okay, once again, I trust that you turned off the video and tried this on your own. Here we've got a slightly different problem. We've got V1 is equal to 200 milliliters. V2 we don't know this time, but our initial pressure, P1, is 101.3 kilopascals. P2 is equal to 106.6 kilopascals. And so I'm going to have here my V2 will equal V1 times a pressure factor. And that's going to equal 200 milliliters. Now, as I go over here, my pressure goes up. So my volume, according to Boyle's law, should go down. So I'm going to put the smaller over the larger. And again, here's where these numbers are really nice. That's 5 parts in 100 roughly. So it's going to go down by 5%. 5% of 200 is 10. So I'm going to say it's 190 milliliters. And I think if you do the calculation, it works out to be that exactly. Okay, so that's how you apply Boyle's law. Now let's take a look at Charles' law. I've sort of thrown this out as like, why does thunder accompany lightning? And lightning, as you're well aware, is an electrical discharge, and it heats up the air really, really quickly. And of course, a heated gas is going to expand. And if it does that, then you are going to hear, or what you're hearing, are the compression waves of the molecules building up on each other. So that's really what thunder is. Okay, so using Charles' law, determine how much a fixed mass of gas will expand if it's heated from 300K to 3300K as typical. Now here we've got a problem. We're not really given V1. You can choose something. You could choose to do this as a ratio or something like that. But V2 will equal V1 times a temperature factor in this case. V1, I just chose, why don't you just choose 1 liter? It's going to be a very easy problem, this one. V2 is going to equal, we don't really know. T1 is equal to 330 degrees K. Remember, there's no little degree sign there. T2 is equal to 3300 K. And if we look at it, as temperature goes up, what happens to volume? Well, hopefully you came up that the volume is going to increase. So my 1 liter, it's going to be the bigger number over the smaller number. And I'll put in my units. And that, you shouldn't need a calculator. It's going to be 10 liters to 2 sig figs. Okay, so that's a very simple one. Let's just go to what we're more likely to see in a problem. Here we go. Here's one. I've actually had some students that went on to become doctors and anesthesiologists, and they say this is something they have to consider. An anesthetic gas is normally given to a patient at 20 degrees C, but the patient's body temperature is 37 degrees C. So what would happen to the 1600 mils that they give to the patient? We don't want the volume to go up too much, otherwise we'd blow their lungs out, and that wouldn't be fun. So again, P1 now, there's a little extra step here, 101, what did I say, 101.3 kilopascals. Oh, sorry, there's no temperature in there. There's no pressure in there, my apologies. V1 is 1600 mils. V2 we don't know. Now T1 is 20 degrees C. But you might remember from your T2 is 37 degrees C. You might remember from your Charles Law lab that the ratios in degrees C, I mean this would almost look like a doubling in terms of temperature, but it's not, because we have to convert this to degrees Kelvin. So to convert to degrees Kelvin, you're going to add 273, so this becomes 293 K, and this becomes 300 K, sorry, 310 K. My apologies. And that's what we're going to use for the factor. So phi2 equals V1 times a temperature factor. The temperature is going up, so the volume, if you recall, should go up. So it's going to be the larger over the smaller, 1600 mils times 310 K over 293 K. That's, well, what's 17 and 300? Let's call it 15 and 300. It's going to be about a 5% change. 5% of 1600 is 90, so it should be around 1690, and I calculated it to be 1693 milliliters. Okay, that's all there is to it. Stop the video again and then go ahead and try the practice problem, and then I'll come back to it. Okay, hopefully you've tried this at your desks, and here we've got a similar type of problem. We have T1 this time is 20 degrees C, 20.0 degrees C, and that's going to be 293 K. We know that in gas laws we have to convert everything to degrees C. We don't know T2 in this case. V1 is 300 mils. Oop, ran out a little bit of space there. V2 is 250 mils. Okay, my T2 will equal T1 times a volume factor. Put in my first temperature, 293 K, and now my volume is going down, so my temperature should go down. So it's going to be smaller over larger, which is 250 over 300, and that should equal 244 K. Now, notice that the question just said what must be done. That would be enough for you to say on a test or an exam or something like that. Leave it like that. It doesn't say convert it to degrees Celsius. Now, if it did say that, convert it, obviously. But if it doesn't say it, leave it in degrees K, because you might make a mistake converting from degrees K to degrees C. How do we get degrees C? Well, we're going to subtract 273 from that, so 244 minus 273 gives us minus 28, and that would be degrees Celsius. That's how you do it, but don't do it unless I ask for it. Okay. Last little bit, again, can these laws be combined? Yes, and this kind of messes up some students, but we can combine all the gas laws if we want. Here's an example. We have a sample of argon gas, that's the one in light bulbs and stuff like that. Pressure of 101.3. So when I go through these, I just start writing things down. So P1, 101.3 kilopascals. Volume is 100 mils, and the temperature T1 is 35 degrees C, which is 273, 308 K. All right, and if we go P2, it says temperature 101.300 mils. What must its temperature be if the pressure becomes, okay, so P2 we know, 96 kilopascals, it's only 2 sig figs. V2 is 200 mils, and T2 we don't know. So T2 would equal T1 times a pressure factor and times a volume factor. So same thing. Nothing different from what we've been doing in the past. But there's nothing that says that each of these factors is going to drive the temperature in the same direction. I think this is where students get sometimes messed up. So we're going to have 308 degrees K times a pressure factor. Well, pressure is going down, so that means the temperature should go down. So it would be 96 over 101.3 kilopascals. Okay, and then we have our volume going up. That would indicate that our temperature was going up. So we would put the larger over the smaller in this case. So one is driving it down, one's driving it up. So if we look at that, then I think we get, let's see, I worked it out, and I got 584 degrees K, which you would anticipate because there's a huge change in volume there. So you would expect a very big number. Okay. On the next page, page 195, you have one more question, and if you'd work that one out by again stopping the video, and then we'll come back to it. Okay, so here's my problem. Will be the final pressure of sampled nitrogen volume. So again, I like to, so V1 I come across first, 950 meters cubed. P1 is 99.3 kilopascals, and T1 is 25 degrees C, which is, oh, there's no zero there, which is 298 K. You're going to see that that's going to be a fairly common temperature that we're going to work at. T2 is 60 degrees, so I think that's 333 K. Final volume, so V2 is 1150 cubic meters, and so we want to find P2. Okay, so P2 is equal to P1 times a volume factor and times a temperature factor. So we have 99.3 kilopascals, and times our volume factor. Our volume is going up, so our pressure must be going down. So it's going to be 950 over 1150. And then our temperature is going up, so that would mean that our pressure should go up. So it would be 330 K over 298 K. And you'll get your answer. I'll leave that to you. Okay, there's your homework. There's some questions there, page 195, 196. I've given you the answers there because I know I'm not here and stuff like that. I just wanted to go over one last thing with you. This is something that we use quite a bit. Sorry, I got that off the camera. What are the standard temperature and pressure? So this is a term that we use in gases quite a bit. It's going to change depending on what we do, but in gases, standard temperature and pressure is also known as STP. Okay, you guys in car racing might know it as a oil additive, but no, it's standard temperature and pressure. Okay, and the standard temperature pressure, this has just changed according to in the IB to 100 kilopascals. Makes things a lot easier. It used to be 101.3 kilopascals. So you're going to see that number quite a bit in the notes. I haven't changed all of them over, but it makes things a little bit easier, except boiling points of water and stuff like that, just a little bit under 100. And then the temperature is 0 degrees C or 273 K. Okay, so here's a typical example of what you might get as a problem on these kinds of things. Gas occupies 100 mils at the pressure and the temperature that you read. What is it at STP? So it's just a really quick and dirty way of assigning your conditions. V1 is equal to 100 mils. V2 they're asking for. P1 is 98.4 kilopascals. P2, because it's STP, is 100 kilopascals. T1 is 300 degrees K. T2, because it's STP, standard temperature is 273 K. You're going to see that this will change depending on what kind of unit we're in, but in gas laws it's 0 degrees C. P2 is equal to P1 times a pressure factor and times a volume factor. Okay, so we have 100 mils times, now our pressure factor, pressure is going up, that means the volume should go down. So I should have 98.4, the smaller, over the larger. And temperature is going down, so the volume should go down, so it's 273 over 300. And again, I could leave that to you. It's about 90 mils, I think, but I'll leave you to calculate that. Okay, and then there's a little bit more on the next page. So that's your application of Charles' law, Boyle's law. You can work on that for the rest of the class. Those homework problems. Remember that the presentation is important, and we'll take those up when I see you next. Thanks very much.